All right. Well, yeah, good morning. My name is Kevin Kuehner. I'm with the hydrologist with the Minnesota Department of Agriculture based in Preston. And what I'm going to do is I'm just going to share some results from a recent study that was just recently published. And getting at this question of how old is the groundwater in southeast Minnesota, and how can we use that information to better understand and interpret nitrate trends in the water. So, a lot of times this question, this question about the age of the water has sort of been overlooked, especially with regard to interpretation of our data. And the main reason for that is that we just simply haven't had a lot of good information on that. A lot of the previous studies have been just sort of telling us that maybe that water is older than 50 years, maybe that water is less than 50 years, but that's about it in terms of our understanding of that age of that water. We know through other things like dye tracing and things like that it can move pretty quickly, but the water that we drink or the water that we see in streams and springs might be a little bit different story here. So I'm going to provide some updates on that. As I mentioned, this was just recently published in a peer-reviewed journal, the Journal of Hydrogeology. The co-authors on that included Tony Runkle, who's the lead geologist with the Minnesota Geological Survey, and John Berry, who's a hydrogeologist with the Department of Natural Resources. There's a lot of people that in the background that have at some point helped in terms of helping inform this process. We had a grant actually with Dr. John Niebuhr with the University of Minnesota through LCCMR funding to contract some work with the USGS to collect some of these age date samples. And then we also worked closely with some researchers at the USGS on that. We compiled a lot of data across a lot of different organizations. One of the big ones here is in Olmsted County, the Olmsted County Lab. They have a lot of great data. And so we worked for probably the last 5 years or 6 years trying to compile a lot of that data for this analysis. So key questions with regard to nitrate in southeast Minnesota that often come up, especially as I work with farmers and landowners in the southeast, is number one is, where are the nitrates trending? So where are they increasing, where are they decreasing, and where are they kind of staying the same? That part is somewhat complicated and hard to do, but what's even more challenging is how do we actually interpret that data? And especially as the previous speakers have mentioned, especially Brad, is the complexity that we have in the southeast is really different. It's really different compared to other parts of the state in terms of the geology, and I'll get into that here in a little bit. And then that last question is, I think, a question that we all want to know, right, is how soon can we measure improvements in the water quality? And basic questions, right, very basic questions, but very challenging to answer in a very simple way. But I'll try to unpack that and try to step us through that process. So the first thing I try to mention to people when trying to address those questions is we have to think about scale. So whether we're talking about at the field scale, whether it's water coming out of our tile drains or coming off the surface of our fields, that can be complicated just looking at that because there can be quite a bit of variability, especially year to year and site to site across the state. But then to try to go to a bigger scale, what happens to that water once it leaves our fields? Where does that go? How does it move? Where does it go in terms of the springs, streams, and rivers, and wells and aquifers? And we also want to think about, if we're talking about individual wells or a kind of a region-wide sort of approach, which is looking at our entire aquifer. So let's get into the trend data right away. So this is results from nearly 1,200 locations across southeast Minnesota. We looked at kind of 3 scales here is what I'm going to kind of talk about. So we're going to look at springs, streams, and wells, and we're going to go through each one of these. These data reflect about 35,000 samples, like I said, collect over nearly 1,200 sites. The trends reflect years between 2000 and 2021, so the last 22 years. I do have some data where I kind of break it down even a little bit further, which I'll go through. I'm going to focus, just for simplicity, I'm going to focus on the springs first. We'll kind of look at that first. And so we see there that the majority of our spring sites, out of these 16 spring sites that were selected here in about an 8-county area in the southeast, 63% of those were increasing. 25% there was no trend, and 13% were actually decreasing. So what's nice about springs, and I really like working with spring data, is because just from an educational outreach standpoint, it's really challenging talking about groundwater, especially something that's invisible, right? It's complex, it's something we don't really think about a lot. But what's great about springs is that this is really where the invisible or the invisible becomes visible. So it's really a nice way to kind of talk about groundwater. And this is a spring in Houston County. It's called Winnebago Spring, and that flows directly into Winnebago Creek. This is another spring in Houston County. This is called Big Spring. I think there's probably about a dozen or so big springs in southeast Minnesota. They all kind of share that name, but this is the Big Spring in Beaver Creek Valley State Park. And if you've ever been in that park, if you drive all the way up to the end of that park, there's this basically a rock with a monument that was put in there probably about 20 years ago. And it says that, it tries to get at this question of, the mystery behind where this water is coming from. And it says, water bubbling out of the ground is a natural wonder. Where does it come from? How long has it been in the ground? And then it kind of goes on to say that they kind of are trying to estimate the age of the water and kind of give some estimates on that. And they say that the water coming from Big Spring has not been in the ground very long. And they kind of estimated that it's probably less than a year in terms of the age of that water. So we'll come back to that based on the data that the new information that we have, and we'll see if that might have to be edited. All right, so let's look at the nitrate data. This is nitrate concentrations in just some random springs here in the southeast. This is 3 of the 13 that I'm going to kind of focus on. The first one here on the left is Fountain West. That's just outside the town of Fountain. That's been monitored through our MDA ambient monitoring program, where we do pesticide monitoring since the early 2000s, but we also do nitrate sampling. So this data goes back to about 2005 for Fountain West. And when I started looking at this data about 10 years ago, I thought, this is great. We're seeing these really nice declining trend in the concentrations. And it kind of made me ask, what might be causing that? Is it because of what the farmers were doing in that area? Or was it some other type of thing that was going on? But kind of the bottom line is with that particular spring is we see a lot of variability. You wait a few years, and now we start to see the nitrates go up. And then now they kind of seem like a little bit plateauing a little bit now. Amherst Spring in Fillmore County shows an actually statistically significant decline in nitrate. And that rate of decrease is about 1% per year. Still elevated nitrate though. Both of these springs are what we consider shallow springs. They're about right around 10 milligram per liter. Highway 76, that's located in Houston County. And that one is very apparent. You don't have to really do any statistics on that. You can just see visibly that that is definitely increasing. And that's increasing at a rate of about 4% per year, or about 0.2 milligrams per liter. So every 10 years, assuming that that rate keeps going on, that's going to increase about 2 milligrams per liter every 10 years. So right now we're at about 5 milligrams per liter. So we're lower than those other two, but based on that current rate, it'll be about 25 years before we get to about 10 milligrams per liter, which is that kind of that rough standard that we go by with regard to some of the surface waters. So what we do know though is there's a lot of variability in these data, and we also know that these differences are not attributable to the land use alone. What's interesting is Highway 76 actually has the lowest amount of row cropping acres compared to Fountain West and Amherst. You kind of expect if you have more row cropping, we might have a little bit different trend there. But so it's telling us that there's some other sort of factor that's going on there. And it's sort of been theorized that this kind of mixing of different age water is really what's kind of helping explain some of this. So it ultimately comes down to what is the age of the water in these systems as one particular variable that we need to look at. So this is the study area that we worked on for the last probably 10 years or so. This is the driftless area, southeast Minnesota. We have about 30 sites that we selected. About half of those were wells and half of those were springs. And I kind of look at that as like we picked 30 trees to understand how this whole forest is working. And we're really kind of using these data to help us kind of extrapolate that out to a much broader area. I want to mention what I'm going to get into now is kind of how do we actually calculate the age of that water. We kind of use two different methods. One is using a discontinued herbicide product, which I'll talk about, and the other is combining that with an independent separate method that USGS has used for many, many years, and that's using atmospheric tracer data. So just a little background on the geology. I know it's been covered a little bit, but I'm going to kind of get into the weeds a little bit on this because it's really important. The geology here largely controls why we see what we see in the water, especially with regard to nitrate. So I've kind of broken this up into we broke this up into really trying to simplify it. And we kind of these three zones or three areas, okay? So if you were in that kind of dashed brown line there, anything to the left of that to the west, that's typically where we have a lot of glacial till material that's typically over 50 feet deep. We typically do not see much nitrate in well water, but where we do pick it up, of course, is in our tile drainage, as Brad was kind of mentioning. As we move further east to the Mississippi, we start getting into these kind of transition zones. We have area 2, which is called the Upper Carbonate Plateau, and then to the right of that black line, we have what's called the Prairie du Chien Plateau. That black line is very important as well, because if you happen to be on the left side of that line or the right side, that can control what happens in terms of what we see with some of the data. And essentially what that is showing is one of the prominent features that we have in southeast Minnesota are these different shale layers, which I'll talk about. And one of those is the Decorah Shale. And that's essentially the area where the Decorah Shale is no longer present, and it's been eroded away millions of years ago. And now we are kind of into deeper kind of bedrock layers that we'll kind of show here. So kind of keep that in mind as I go through the charts here, whether we're in, and I'm going to focus on area 2 and 3, and just kind of keep that in mind when you look at the data. These are the 13 study springs that we evaluated. All right, a little bit more on the geology. So if you kind of had to draw like a slice through the earth, and we're looking at a cross-section across southeast Minnesota, kind of starting in, this is area 2, so basically kind of think of Highway 63 on east to the Mississippi. Area 3, I kind of use like if you're like in Fillmore County, Highway 43 would be kind of a good example. Everything kind of to the east of that is you're starting into that area 3. So we have these various layers of rock, and these are the kind of the locations. We can kind of break those springs up, those study springs, into kind of 3 main areas. We've got Group A, Group B, and Group C. Group A springs are kind of those shallower most springs. Group B is kind of lower in those rock formations, and Group C is the lowermost, kind of in those deeper formations. The thing I want to kind of also mention here is that kind of the brown lines, the horizontal lines there, those are what geologists call aquitards. Another term for it is a confining layer. And these are basically layers of material that don't prevent the water from getting down, but really hinder the downward movement of that water as it travels through those different layers of rock. Again, a really good example of that is the Decorah Shale. You can see that actually along Highway 52 in certain areas here in Rochester where it's kind of exposed. And those, again, have a really strong impact in terms of how we interpret the data here in the Southeast. This is quite complicated in terms of once that water gets in the ground in terms of where it goes. This is what we talk about the hydrogeology. So how does that water move once it gets into those different rock layers? It's complex, but basically what you're seeing here is that water is, you have water that's going to move through those different layers of rock that's going to recharge really quickly to our aquifers. And then we have what we call this predominant flow of water, which is going to kind of move sideways. Generally speaking, the groundwater in southeast Minnesota wants to make its way towards the Mississippi, but as we get towards kind of western Fillmore County, kind of the divide there, it wants to kind of move its way towards Iowa. Essentially what it's trying to do is it's trying to find through gravity and under pressure in certain cases, it's trying to find that lowest elevation. and it's trying to make its way to its nearest stream, river. In this case, it's trying to make its way to the Mississippi. So it's complicated, and I'm not a geologist. And so one of the things that we did about 7 years ago or so, I kind of pitched this idea of creating some educational videos about how groundwater moves in the Southeast. Instead of me trying to wave my hands all the time and try to explain this stuff, let's create some animation, some video that could do that. We were fortunate to get some funding from Minnesota Corn Growers and the Pollution Control Agency, combine those funds, and put together a project that created these videos. Interestingly, we had a short 2-minute video that we talk about karst, and right now I think it's over 200 and some thousand views for that one 2-minute video, which is pretty remarkable to me. One thing I want to kind of notice here, we got the sinkhole up there. You know, that's a very prominent thing that we talk about in the Southeast, that sinkholes. They're a very dramatic feature in the landscape and very important, and we need to make sure we pay attention to those. But from a nitrate standpoint, this is not the primary mechanism for how nitrate moves. Just as Brad mentioned, it's primarily leaching is that main mechanism throughout the entire landscape where we see nitrate move through these systems. And in the video, we highlight this concept of lag time, or this idea that there's kind of a delayed response in the water. And we kind of introduce it in the video. And I give this example of Bridge Creek. This is another stream in Houston County. We've been monitoring this very intensively since 2010. And the first probably 3 or 4 years, we began to notice this very prominent pattern in the data in terms of what it was doing. And it sort of, again, highlights, similar to Highway 76 spring, that there's something going on here in terms of these trends. So that really kind of introduces this concept of age of water, or residence time, which is what geologists and hydrogeologists like to describe it. It's essentially the amount of time it takes for water to travel through the surface, both snowmelt or rainwater, to travel through those different layers of rock, and eventually make it to the point that you're interested in, whether it be a well, a spring, or a stream. Now there's other kind of terms for this. Some people may call it travel time, again, lag time, or age. I typically just kind of use age just to simplify it, but really the technical term is residence time, because it's the amount of time that it takes for that water to move through that soil. When we talk about age, some people may interpret that as the age of the water itself, going back, millions and millions of years, but we're not talking about that. We're just talking about the amount of time it takes to move through the system. So that water is complex. Once it gets into that rock, it can make a lot of different pathways in terms of where it's going to go. Take, for instance, a rock face, a quarry face in Southeast, a typical rock quarry face here. We have what we call this triple porosity system, where we can have that water move very quickly through fractures and conduits. And those fractures and conduits have been enlarged over millions of years because of a chemical reaction with the rock, where slightly acidic water is dissolving away that rock over time and making those passages bigger. That's why we have the caves that we do in the Southeast. But we also need to talk about the pore spaces. This is what we call the matrix, similar in soils, similar in rock. That's basically when all that rock is filled with water, all those pore spaces are also filled with water. And that water though can move very, very slowly over time. So you got this mixture of variable flow paths. And the other thing to kind of really highlight here is when we take a water sample, whether it be from a well or a stream or a spring, really that water sample represents a mixture of all of those ages together. So a single groundwater sample represents that mixture of different ages, and that mixture consists of many discrete particles that are moving at different speeds. Some of that is moving pretty fast, some of it's moving kind of slow. But it's that mixture is what ultimately drives the quality of that water. So what scientists do, especially with USGS, is what they do is they recognize that the tracers that we have to estimate the age of the water, some of those are only good until like post-1950s on, and some of them we just don't know. And so we have to kind of make some estimates using some modeling. And they kind of try to figure out essentially with that model to estimate what fraction of that is younger water and what fraction is older. So this is a really nice diagram I like. This is from USGS, just really simplifying this concept of that, this water is a mixture of ages. We tend to have that really young water near the surface. And as we go down in those different layers, we're going to have older water. Some of that water can be hours, days to years old. And some of that older water, as you get deeper in that system, it's going to be decades, centuries to thousands of years old. How do we actually know the age of that water, though? So one method is dye tracing, and this has been done quite a bit extensively by the Department of Natural Resources, along with the University of Minnesota, placing dye in sinkholes and then putting charcoal packets in certain locations in springs, especially, or streams, and then measuring the concentration in those packets in terms of trying to figure out where that's going. And in those studies, if you're above those confining layers, in those really shallow areas, we find that that water travels miles per day, which is extremely fast for groundwater in southeast Minnesota or in any groundwater system. But that only gets at that really young water age. So then we have to rely on more sophisticated, more expensive methods, which is using atmospheric tracer methods. And this is kind of the standard for measuring the age of groundwater. And one of the kind of tried and true methods is using tritium. Tritium is a natural product that you see in the atmosphere, but unfortunately, because of our testing that we did in the 1950s and 60s globally with nuclear testing, that tritium got into the water cycle and it got into our water. We know that when that was first introduced, we knew when it peaked, and we know when it is no longer being, basically when the concentrations are going to be near zero. They can use that to estimate the age of the water. There's similar techniques for CFCs and other sort of products that are used in industry that get into our water, and they can estimate the age based on those tracers. For that really old water component, we have to use carbon-14. Carbon-14 is kind of a standard for that really old water. Kind of the bottom line with all these methods, though, is they all have their limitations and advantages. But and also, to gain confidence in the data, we also need to kind of use a lot of different tracers to make sure that we know that that age is actually that age. One thing that I've been really exploring the last probably 10 or 12 years has been this idea, could we also try to, because these are very expensive, they run about $10,000 per water sample if you're going to do atmospheric tracers. We can't do that a lot, right? So could we try to maybe double the amount of samples that we have by just using existing data sets that we already have in our data set? And one of them is using data from a discontinued product, a pesticide product called Alachlor. Many of you guys are probably more familiar with the trade name Lasso. This was a product that was first introduced in 1969. Its usage really climbed dramatically in the 1970s. It peaked in about 1980, and then we had this really strong decline throughout the 1990s. And then really the effective end use was in 2000. It got pulled off the registration in Minnesota officially in 2016. But this really kind of makes kind of an ideal tracer in terms of trying to age the water, because we know the pattern of the data, especially when it was the product of when the product was used. The other thing about Alachlor is one of the most common degradates, or kind of the byproducts of Alachlor, is it breaks down pretty quickly once it gets into the ground and in the soil and in the water. And one of those products is called ethane sulfonic acid. And that has sort of conservative properties once it gets in water. So it basically kind of stays in that form. So it's not some biological process that's going to convert it and confuse us in terms of how we try to age the water. All these methods have different limitations. The one thing with Alachlor, using Alachlor, is because it was introduced in 1970, we can't estimate what might be that older fraction of water, but I'll kind of get into that here in a little bit. So what do we see for Alachlor ESA in these study springs? What's very interesting, and you don't have to do any fancy statistics when you just look at the data here. We have not used Alachlor for over 25 years, but you'll notice right away that some of these springs are showing this very strong increasing trend of Alachlor ESA byproduct in that water. These are very low concentrations. These are in parts per trillion. But kind of the point here is that we're seeing this pattern in the data, and that's really important for us to interpret what's going on here. we'll see in Spring Creek Spring or Burr Oak Spring, we see kind of a linear decline there, but in Burr Oak, we see more of like an exponential type of decline. And then in Highway 76, we see this very strong increasing linear trend. And then in Big Spring and Peterson, we're actually at or near peak for those concentrations. So again, kind of going back to Big Spring, that's a really big clue for us that we know that that water is definitely a mixture of water, not within a year old, but it's definitely much older than that, because just simply that we're just near peak in terms of those Alachlor ESA concentrations. So let's look at the data in terms of what we found for the results. And this is just sort of, I don't have them organized at all. I'm just kind of showing you what the range of values we have in years for these 13 study springs. We see that the ages range from 12 years up to 41 years for the age of that water. Now, this is where the geology comes very important, where we can sort these data by the relative, what would they call a hydrostratigraphic position. So remember I showed you before on that map, the A, B, C springs, higher, shallow springs, lower, deeper springs. Let's organize the data now by that. And this is where I was kind of really hoping that this is what it would look like. And if it didn't, I knew at that point this methodology would not work, because our methodology assumes that as we increase in depth, we should see sort of this increasing age of the water. And this is exactly what we're seeing. So as we organize the data from shallow springs to deeper springs, we see that we have older water as we get into those deeper systems. So we're ranging from about 1 to 2 decades up to 3 to 4 decades in those deeper springs. We can also use kind of a separate but related sort of approach, which is using the elevation of the spring itself versus the elevation of the recharge area to that spring, and the average of that, and just kind of similar to like the depth of a well, and plot that data. And again, we see that as we increase in depth, we increase the amount of age of that water. All right, now let's add in the Alachlor data, the Alachlor ESA concentration data. And this is very interesting, because what we see here is a lot in those shallow springs, we see the concentrations are lower, right? In the deeper springs, we see, actually the really deep springs, we see even lower nitrate or Alachlor concentrations. But then we kind of have this sort of spike and kind of in the middle there in those deeper springs. And essentially what this is showing is this is kind of the wave of that Alachlor ESA as it migrates through those bedrock layers. We're starting to pick that up. Now we can layer in the trend data. So these are the actual statistical trends of what that Alachlor ESA is doing. Where is it going up or is it going down? And we can see there that those shallow springs are all going down. The deeper springs are going up. And then we see those that still are probably right at or near peak. All right, now let's layer in the nitrate data for those sites. So this is showing the concentrations of the nitrate. We see that our highest nitrate concentrations are in those shallow springs. A lot more variability though. So the longer that bar is, the more variability that we see. Less variability as we get in those deeper springs. And then when we layer in the trend data, again, this is kind of a really important point in the whole data analysis part. Was like, okay, this is very interesting, because what we're seeing is this very, very strong pattern where the increasing trends of nitrate a lot of those are in those deeper settings. And it's increasing at a rate of between 1 to 4% per year, which equates to about 0.1 to 0.2 milligrams per liter per year. So again, every 10 years, we're increasing about 1 to 2 milligrams per liter. And this is going to continue, right? This will continue until it kind of gets into a balance with not only, the current land use that's in that area. So now we can kind of look at the relationship between kind of all these different methods. This is both wells and springs. And you're just seeing basically what the take-home message here is, that as we increase in depth, we're going to increase the age. And we increase the age for every 100 feet, we're increasing the age by about 6 to 8 years. We also find, and I don't have this shown in the chart, but we also find that as we increase in depth by about 100 feet, we're decreasing our nitrate by about 3 milligrams per liter. And then the other thing I just want to kind of point out is that this is pretty remarkable in terms of the agreement that we're getting between these separate independent methods. So that gives us more confidence that these data are actually kind of telling us what they're telling us. And one example, we had a paired where we did the two different methods, the allochlor method and the atmospheric, and they came in within about 4 years of each other. And I was hoping we'd get within 10, and that was within 3 to 4. So I felt really confident that, yeah, this was something that we could actually use to estimate the age of the water. Again, kind of what we see here what this is basically showing is that as residence time increases, that kind of probability of finding an increasing trend increases as well. And then this is kind of pulling all the data together, all the different methods. The bar chart on the left here is kind of showing the range of ages that we have. And again, this is one of the limitations we have with some of these tracer data is that we can only, for instance, tritium didn't start happening until the 1950s. So we don't know that mixture of water previous to that. So we kind of can use a different method to kind of estimate that older fraction, and that's what USGS helped us with. And that kind of, for a subset of those wells, we find that increases the age even a little bit more, up to about 20 years or more. So some of that water may be even 3 to 8 decades old. Then there's kind of a group of wells where we don't detect any of these tracers, and we also do not detect nitrate. So several years ago, Dr. Calvin Alexander, who's been retired now for several years, he and Scott Alexander did a bunch of testing of these wells that had no nitrate and also had no other tracer information on them. And they did a wide variety of wells where they sampled it for carbon-14, and what they found was, on average, we took a subset of that data and kind of organized it just for our kind of study area. And when we looked at that data, out of 135 wells, we found that the average age of that water using that carbon-14 technique was about 7,000 years old. So given all of that information, we then have to kind of think about if our water is indeed, some of that water in certain aquifers is indeed older than, let's say, several decades old. We then kind of have to go back in time to kind of interpret that data. So what this is this is a couple of charts here that you're seeing kind of historical land use here in southeast Minnesota going back to about 1920. This is NAS, National Ag Statistics Service survey data. And then on the bottom is commercial fertilizer sales data that we have across the state. So kind of making the assumption that sales data across the state is representative of southeast Minnesota, we can kind of look at the patterns of this data and kind of compare it. But if we're looking at water that might be 3 to maybe 6 decades old, we kind of have to look at what was happening around that time. In the 1960s and 19 through 80, that was really a dramatic kind of increase in the amount of corn acres in the southeast. In the 1980s, that was a dramatic increase in the amount of soybean acres. But we have been noticing this pretty consistent trend in our hay and alfalfa acres. Since about 1980, we've been declining by about 2 to 3% per year. We also have to kind of think back again, if you're, let's say, 4 to 5 decades old, 1960s, that's the time period when our commercial fertilizer was really ramping up in terms of production and people using it. My father's been farming now he just turned 88, and he remembers his first bag of fertilizer that he used on his farm was in about 1960. So it makes a lot of sense that, we really started to see that increase in terms of widespread adoption of commercial fertilizer was around that time. Now that's for that older water component, but we also, for that younger water component, we have to also think about weather and how weather and precipitation could affect the interpretation of the data. And this is just a chart just showing kind of the trend pattern that we're seeing for our precipitation. I'll get into that here in a little bit in more detail. All right, so kind of covered the springs and the streams and the age of the water a little bit. Now let's move on to the stream data. It makes sense that in our stream data, if what we find in our springs, we're probably going to find in our streams, because about 80% of the flow that you see in the streams in southeast Minnesota is essentially what we call base flow. That's basically all the flow that's coming during non-storm event conditions, and essentially it's the groundwater. And so what we see here is very interesting that over 50% of those stream sites in southeast Minnesota were increasing. The other thing I want to point out is we had 22 sites in northeast Iowa that I also analyzed that were separate and independent of this data set, and they were seeing the same thing basically. This is kind of the point where probably Tony and John were really rolling their eyes at me, because I said, let's not only look at southeast Minnesota, but let's look at the glacial till area outside of the driftless area. So this would be like, think of Le Sueur, the Blue Earth, anything kind of south of Mankato, those heavily tile drained watersheds where we know that water is very young because it's mainly tile driven systems. And what we find there is that majority of those sites were decreasing or no trend at all. So very different than southeast Minnesota. So this is a map showing those watersheds and the stream trends that we've been seeing. And we see this pretty consistent pattern with all the increasing sites in southeast Minnesota. We only had one site in what we call this like heavily tiled drainage area that was increasing, but the rest of them were either no trend or decreasing. I kind of took it a step further and then said, well, what about during a really wet period, especially between 2012 and 2021, that 10-year period? And we see a lot of those watersheds that were either no trend, they basically went to decreasing. So this is just kind of showing that we had a lot of those sites. There's a big change in the amount of trends between those two different time periods. And this is kind of just showing which of those watersheds were changing the most. So a lot of these were going from no trend to decreasing. So the question is, well, what is causing that? Again, I want to point out area 3, kind of to the right of that dashed line. Those watersheds, despite the change in that wet conditions, those pretty much remain the same. They remained increasing. So that's kind of telling us again that older groundwater component has a very strong dominant influence on the trends. But these watersheds that have very young water, again, what is causing that? And so, again, going back to our precipitation, this is a chart that I put together. This is data from NOAA, and this is showing what's called the Palmer Hydrologic Drought Index. It's showing areas of time periods where it was really dry and areas when it was really wet. And what's really nice about this data set, this goes back all the way to 1895. And what's also nice about this data set, it doesn't factor in normals. It's just sort of saying, based on the hydrology and the hydrologic conditions with this index, it's saying when was it dry and when was it wet. And I just kind of put a reference there of the Dust Bowl in the 1930s, kind of in reference. We think the last few summers have been dry, nothing in comparison to what was going on, of course, during that time period. But what is very interesting is when you look at the data, that time period, 2012 through 2021 that we kind of analyzed, that was 5 of the 12 wettest years in the past 128 occurred consecutively between the year 2016 and 2020. So very wet. I know many of you that farm, I don't have to remind you about that, how difficult it was to do any field work and things like that. But again, that's probably the big driver for what's kind of dominating the trend. But I don't want to disregard the practices that farmers have been doing also. And, Brad kind of mentioned some of those, and there's, a long list of those sort of things, some of them being plant genetics, better rooting systems, maybe improving some of the nitrogen use efficiency, how we apply our fertilizers, soil health practices, even regulations and programs, of course. And then, of course, there's, future advancements that, could be taking place. The challenge with this data set, and this was kind of beyond the scope of our project, but the challenge with trying to analyze this is that it's kind of all over the place in terms of where do you get access to this information. And so hopefully that will improve over time. We'll have a better record of this, but because of the challenges with how old the groundwater is, we may have to think about this as another metric of how we kind of measure our performance over the near term. All right, to kind of wrap things up here, I'm just going to quickly go through the well trend data a little bit. Wells are intentionally constructed to avoid that old or the recent water, right? So we talked about the well code a little bit. And so out of this subset of wells that we found, it wasn't surprising to me that we found a lot of these sites, number one, had no detection of nitrate, 34%, or there was no trend. But we did have 13% that were increasing and 4% that were decreasing. And I think the best way to describe wells is kind of give some scenarios, okay? So let's just say you happen to have a well and you live in area 2, all right? And let's say that well is 150 feet deep. We would be above the Decorah Shale. And let's say that that well was constructed prior to 1974. So we would not have grouting and casing on that particular well. We would expect to see high nitrate, definitely above 4 milligrams per liter. That's typically what we see in those systems. We may even see nitrates as high as in the teens or even higher. It really varies depending on the land use in that area, but that would not be uncommon. For our trends, we would not expect to see any trends. Sometimes, occasionally, we may even actually see a decreasing trend. Maybe that's due to the weather, maybe it's due to land use, but that's typically what we may find. I do want to kind of mention, though, that there's always exceptions to the rules. There could be always something that's going to deviate from this. We have the second well, we could have a well right next to well A, and that's going to be a bit deeper. Now we're into what we call the Prairie du Chien, into the Oneota. That's below the Decorah Shale. Let's assume that that well is cased and grouted. It's a newer well. We would expect not to see any nitrate in that well. And in fact, our data shows that that water is probably thousands of years old. Well C, we could have another well, very similar location. That well is 400 feet deep, pre-1974 construction. So it doesn't have that case and grouting. We would expect to see variable nitrate, so up and down, and we also see variable trends. Some of it going up, some of it going down, but quite a bit of variability. If you're in area 3, so this is in that, what we call the Prairie du Chien Plateau, kind of think of Highway 43 in that area. If you're in area 3, you typically are probably gonna be in the Prairie du Chien or the Jordan. Your well is gonna be probably about 280 feet deep. And if you probably are going to have it cased and grouted. And in this case, we're probably going to find medium nitrate, probably in that 5 to 7 range. Could be higher, could be lower. But what we probably are going to find is that water is going to be older than 30 years old. And the other thing I want to highlight here is we have a higher risk for an increasing trend. And this is where we find a lot of that data. Again, there's always exceptions to this, but what we tend to find is in this kind of dashed area, in area 3 especially, I think Brad kind of showed it in a map. We're kind of seeing this, a lot of the townships that are testing high, kind of following a northeast to southwest diagonal. And this is kind of that area where we're kind of in this high risk area where we may have a higher risk for nitrate and increasing trends. And one of the main reasons for that, you kind of ask yourself, well, why is that? We're kind of below that Oneota aquitard. Well, geologists will tell you that Oneota, it is an aquitard, but it is also can be very leaky. And leaky in terms of, it takes maybe 30, 40, 50 years for that to kind of move through that system. Again, it can be quite variable though. That Oneota is not the same everywhere. So, and then the last well would be well E. That would be 550 feet deep. Very similar to well B in a way. You probably are going to not have any nitrate, and you're probably going to be very old water. We hope to try to develop something that would kind of help homeowners and landowners kind of do this on their own to kind of estimate like what aquifer are you actually drinking your water from. I think probably most of us probably don't even know what aquifer we're drinking from, and so we're hoping to kind of develop something like this that can give insights to homeowners and farmers about actually some of these details. All right, to kind of pull it all together, we can develop a conceptual model based on all this information that we have. We can say that this is the age of the water in southeast Minnesota. We're going to have younger water near that edge, and especially above those regional aquitards. But as we get deeper and lower and away from those kind of deeply incised valleys, we tend to have much, much older water. We can then look at the nitrate data, the concentration data, and we see kind of reverse of what we saw for the age of the water, where the higher nitrate water is near the surface or near the, those shallow-most areas. And again, we're going to see some areas that have a higher risk for elevated nitrate and increasing trend. So if you're taking a water sample, these are some of the things you got to think about when trying to interpret that data. If that water primarily comes from above that black line, you have to think about that water is probably less than 20 years old, and you have to think about recent nitrogen inputs, how we manage the land, and also the variable precipitation patterns. And that's probably one of the bigger drivers that we have to kind of factor in, because that can have a big impact on the data. If you're below the black line, in terms of where you're getting your water, where you're collecting the water, you have to think about historical practices, historical land use changes, and also dilution from older groundwater. All right, so kind of in summary, it's complicated, but so we have this combination of decadal time lags, legacy nitrate, historical land use, weather variability. All those things really complicate our ability to interpret the data. But what we can say is that we do know there is quite a bit of younger water out there, and we know that that's probably typically less than 20 years old. It has high nitrate, typically higher nitrate levels. But in terms of the trend, it seems to appear that we're relatively stable and pretty much in equilibrium with the current land use. And sometimes, in some cases, it's declining, whether that's because of land use or if it's because of weather. Those are factors you have to kind of think about. But in certain aquifers, and this is kind of the take-home message here, in certain aquifers that have older water, okay, that's older than 30 years old, nitrates are lower, but they're slowly increasing. And this increase is going to continue. So regardless of what we do today, unfortunately, that nitrate, the train has left the station. It's going to continue to increase. And it's trying to get in balance. Anything in Mother Nature wants to get in balance, and that's what it's trying to do. It's trying to get in balance with the current land use and the historical land use. Now, with that said, that doesn't mean that we just kind of throw our hands up and feel deflated, right? So although it may take more time to measure the impact of these clean water activities in certain aquifers, the cumulative effect that we all do, the collective effort that we do, will make a difference, and especially the loading to these aquifers over the long term. So in summary, kind of rounding about, going back to Big Spring. So if we had to make an edit to that plaque, this is kind of what we would say, is that water coming from Big Spring is a mixture of water that dates back at least 3 decades old. That's what I've got. Thank you. So the question was, how do you try to find a lot of this information for your own situation? Again, we kind of have to look at groundwater as a 3-dimensional type of thing, not just a two-dimensional. Minnesota Geological Survey, they've done some work in the Zumbro River watershed and a few other study watersheds where they've been trying to create some kind of 3D interactive mapping tools for people, which is great. And they're actually working on that right now in the Root River watershed. We've been kind of talking to them about this idea of how can we make it even more useful for homeowners, and this idea of trying to create, essentially that map I was showing you before, where it could kind of bring that into maybe an application on your phone or a web type based service that would kind of say, hey, if you know the depth of your well, and we know the location, we could probably get some really important insights from that information. So yeah, I agree. I think there's a lot of data out there. It's just like, how do we make it more useful so people can actually use it?